In the last video, we saw how to declare variables and use operators to do math on those variables. In C++, we call each of these instructions a statement. Any program can be written just as one long sequence of statements, but it would be very difficult to keep track of everything and work with other people in the same codebase. Luckily, we can organize all of these statements into higher level structures. The first tool that we have for organization is the block. A block is just a sequence of statements enclosed by curly braces. There's not much we can do with just blocks, but they're important because they let us control multiple statements of code at once in C++. Things start to get really useful when we can give blocks of codes names and define their input and outputs. We call these functions. Functions let us package up a block of code with a name so that we can invoke it anytime within our program. And we refer to invoking a function as calling it. To define a function, we need four things: a name, a parameter list, a return type, and a body. The function's name is an identifier that we can use to refer to the function. Check out the previous video for the rules for C++ identifiers. The parameter list and return type tell the computer what the input and output of the function are. They allow us to actually get data into and out of functions. And the body is just the block of code that will execute whenever the function is called. Now let's look at an example function. So here's our example function. Let's break down the four parts of this example. Our identifier, or name of the function, is right here, %a of total. Our parameter list goes in the parentheses to the right of the name. In this case, we can see that we have two parameters, both of type int, called part A and part B. Our return type is the type to the left of the name. In this case, it's double. And our body is the block of code that follows the first three parts. This particular function takes in the counts of two populations, part A and part B, and calculates what percentage of the total population part A makes up. And in this case, the body just needs to be a one-line formula that does that math for us. You may have noticed a new keyword in the function body, return. This keyword terminates the current function and yields the given expression result as the output of the function. This means whoever called the function gets this value as the result of calling that function. So if we were to have another line of code that actually called our %a of total function and stored its result into a variable, the value of our return expression would get saved into that variable. Note that return will terminate the function's execution regardless of where in the body it appears. So in this example, when our first line of our body is return and we have a line after that, that second line will never actually run because as soon as the return line is done, we're out of this function. What if a function doesn't need any input? For example, we have this incredibly useful function, always return 10, that, surprise, always just returns the constant 10. It doesn't need any input to do its job. Well, we can simply leave the parameter list empty. And that tells the computer we don't need any input to run this function. Now what if a function doesn't provide any direct output? We can't leave the return type slot empty because then the computer won't recognize this as a function declaration. So we need some way of saying there's no type here where a type is expected. And for that, we have the void keyword. Void is a special type that is formally defined as having an empty set of values. This just means that void represents the type of data for nothing. There is no piece of data or information that is accurately described by the void type. The most common way that it is used is to specify that a function doesn't return anything. If your function returns void, you don't even need to have a return statement. The function will terminate when its body ends. Any return statements you do have can't have an expression associated with them because there's no data that you can give through a void variable. There are some non-function related uses of the void keyword, but we'll save those for later. The last thing we need to talk about functions for now is scope. There is a practical limit to how many unique names humans can come up with to refer to different pieces of data. With all the standard and community written libraries out in the world, it's easy to imagine that there are a lot of variables out there with the same name. Scope rules are how we avoid having problems with multiple variables with the same name. Formally, a scope is a portion of code, sometimes discontiguous, in which some name is a valid identifier. All variables are declared in a scope, and outside of that scope, that variable name is meaningless. In practice, blocks define new scopes. So, for example, this snippet of code has two scopes in it. We have one scope that includes the entire example, and then we have a nested scope defined by this single line block of code in the middle. So in the first line, we declare a new variable a, and set it to the constant 10. The next line starts a block, and so it starts the nested scope. We declare a new variable b and set it to the same value that a currently has. We're allowed to do this because you can always reach into a parent scope. So now b and a are both set to 10. The next line closes our block and thus closes the green scope. B now no longer exists. Because its scope was finished, it's been destroyed. And that's problematic for our last line of code, where we say a equals b. We're back in the blue parent scope, and so every variable that was declared in the nested scope no longer exists. So when the computer sees this reference to b, it's going to fail to run our program because it doesn't know what b is. B doesn't exist in the blue scope. Scopes are important for functions because function bodies are blocks, and so they are their own scopes. Any variables declared inside a function body don't exist outside of that function body. In the long run, that's really helpful so that we don't accidentally mess with data we didn't mean to touch. And that's all for functions. We now have ways of organizing our code into reusable, nameable blocks. Instead of commenting some portion of our code to explain that it uses such and such algorithm to do a task, we can package that section of code up into a function with a descriptive name and well-defined inputs and outputs. In the next video, we'll use this new tool to move away from the short examples we've done so far and show how to put together an actual C++ program that we can run.